The second and the third part of this lesson concern specific techniques to calculate the antiderivatives. First, we're going to key upon elementary functions, that is, algebraic functions and some simple exponential functions. We're going to key upon these three rules. The power rule, add the power by 1 and divide. That doesn't work when k equals to -1 because denominator is 0. In that case, x to the first power is 1 over x, so we have logarithmic function. Exponential stays the same. Those are the three rules. We can extend these rules using the chain rule when the inside is just linear function. For more detail, please refer to the first part of the lesson. Let's begin with some simple example. How about this one? Well, okay, just too simple. Let's move on to the next one. Well, this one, the 5x to the fourth power is typical power function. So we're gonna increase the power by 1 and divide. It'll work out. How about the next one? This looks like products of two functions. However, it is not. It's actually a single power function. X to the first power is here, times x to the 1/2 power is there. So putting those together, 1 plus 1/2, this is x to the 1.5, or x to the 3/2 power. How about this one? E to the 4 power function, or exponential of 4 function? Neither. This is just a constant. There's no x in there, so e to the 4th power is just a number. Keep those in your mind, and we can calculate the antiderivative like this. Let's see, increase the power by 1, 5 was there before, and then divide by 5, and we end up with 5 over 5, so we have x to the 5th power. How about the next one? Increase the power by 1, so we have 5/2 power, and we have to divide, which means we have to multiply the reciprocal, and 2 was there before, so calculating this, -2 times 2/5, we have the number we had before. And then e to the 4th power, that's a number, that's a constant, so times x. Here we go. Let's go to the next problem. How about this one? We have product of two functions, so how do we calculate the antiderivative? Well, very last thing you should do is something like this. Calculate the derivative of the first function times the derivative of the second function, or excuse me, antiderivative of the first times antiderivative of the second. It doesn't work like that because the derivative of product is not product of the derivative. We have the product rule instead. But for product rule for antiderivatives are far more complicated. So what we do, we use brute force. Simply expand the integrand by breaking up all the parentheses by foiling, and we have a bunch of power functions added together. And then we can simply apply the power rule one at a time. The same philosophy applies for the second problem. The next problem, excuse me. This second power here can be easily broken up by foiling or complete square. Once you do that, you have a bunch of power functions. Easy from this point on. A little bit more complicated case is like problem E or F, where we have to consider some fraction. Unlike part C, where I rarely see mistake, I see a lot of mistake from these kind of problems. A lot of students take the derivative of numerator and the antiderivative of numerator over antiderivative of denominator here. That's not the way. Just like part C and part C did not work like that. How do we do that? Well, solution 1 is our textbook's method. First, separate the numerator. We can do that because denominator is just monomial. and then simplify each fraction. 2 minus 1 is first power, 1 first power. X cancel out. 1/2 minus 1, so negative 1/2 power. Now that we have a bunch of power functions added together, we can apply the power rule one step at a time, and we have an answer. Solution 2 is similar, but we use different step in different idea in the very first step. Instead of separating the numerator, change the division by 3x into multiplication. This 3 in denominator is a number, so it stays there. X in denominator, x to the first power in denominator, can be flipped over to the numerator by x to the negative first power. If this had been x to the second power, like this problem F, then this will be negative second power, and so on. Now that we have multiplication, we can just distribute this multiplication, and that's gonna give me a bunch of power functions added together, same as before. Consequently, we can apply the antiderivative rule for power functions one step at a time, and we get an answer. Pretty similar problem is repeated in part F, and that part is left to the students. Now let's talk about exponential functions. For warming up, let's talk about the first problem here. This one looks like, well, rather confusing because there are too many x's and e's. However, only the first function is an exponential function, e to the x power. X to the e power, that's a power function, where k value is e. E to the e power, there's no x, so that's just a constant. X over e is the same as 1 over e times x, so it's a linear function. E over x, that's a reciprocal function, x to the negative first power. Consequently, we are going to have something like this. Exponential, power function, constant times x. First power function became second power function. Reciprocal became logarithmic. Okay, the first problem was just more confusing than theoretical. So let's go ahead to the second problem. It requires a little bit more thinking here. Just like problem E and F in 2.3, we'll have to do some manipulation in integrand because we cannot work on fraction right away. The first method, the textbook's method, let's separate the numerator. And then simplify. This can be a little bit tricky, and some mistake-prone students may have to be really careful here. 2x plus 1 minus 3x plus 2, so you have to be careful calculating because sign mistakes are rather common. 2 minus 3, negative 1. 1 minus 2, negative 1. All these are subtractions. Now that we have e to the ax plus b form, we can apply this antiderivative rule for exponential function, this extended rule for appropriate a values to find out the antiderivative. What's the first one? 1/2 was there before, and then we had to divide by negative 1 because a value is negative 1. Of course, the simplification yields negative 1/2 here. How about the next one? We used to have negative 2 down here, and then we need 1 over negative 2 because a value is negative 2. A simple cancellation, negative 2 times 1 over negative 2 yields just plus 1, so this becomes just plus. How about the third term? Well, we used to have 3/2 there, and then by this antiderivative rule for exponential function, we need 1 over a. A value is -3. And then a little bit of simplification. This 3 cancel out and sign change. We are going to get -1/2 as before. That's solution number 1. How about solution number 2? I like solution number 2 a little bit better because I find it a little bit easier to do addition than subtraction. Here, instead of separating the numerator, I flipped the denominator over to numerator by changing all the sign. So far so good. Next, when I distribute this e to the -3x minus 2 to multiply over, what I need to do here is addition. -3 plus 2, -2 plus 1, generating -x minus 1 instead of subtraction. If you have too many negative signs flying around, additional subtraction can be confusing and tricky. Consequently, I like the second method a little bit better, but the preferences, the choices of the students. And final computation is same as before. It's exactly the same type of problem. I have one more problem here in part C, which runs pretty much the same as 2.4b, which we did. I'll leave this one to students. Because there are some negatives, it can be a little bit trickier. And advanced warning, there's one trap that you have to beware. Now let's move on to final type. These are the kind of problem that you really have to understand the meaning, the role of plus c. We have a derivative, and then we have a specific function value, which we call initial condition, and we have to determine the original function. Let's go with part B. Determining a function from the derivative is just antiderivative computation. Integral. So here we go. 1 over square root of 2x plus 3 is equivalent to 2x plus 3 to the -1/2 power. And exponential 2x minus 1. And then what we do, let's apply those antiderivative rule there. So what we have here, -1/2, and we have to add 1 to the power, so 1/2, and we have to multiply the reciprocal, so we have to have 2 over 1, and then we have to divide by this 2, so we have to have that as coefficients. So I'm afraid there's a typo here, so they cancel out to just 1. I'm glad I just found out. And that exponential function remains the same. Okay. Now this is f of x. What I need to do now is to determine what c value we have. That's where this initial condition is being used here. Let's correct this error here. Plug in x equals to 1/2, then 1/2 times 2, that becomes 1 plus 3, and then plug in 1/2 there, we have e to the 0 power. So what do we have? Square root of 4, so that's 2 minus 1/2 plus c, so that should be equal to 3/2 plus c, and that has to be the same as 1/2, the given condition. That's how we can identify what c is. C, flipping over, c is -1. Now that we found out c, we can plug that value in to determine my f of x. Here it is.